High-performance CPUs and GPUs generate intense heat under heavy computational loads. Every action performed on a computer, from rendering complex graphics to running intense gaming sessions, requires billions of transistors inside silicon chips to switch state rapidly. This flow of electrical current generates intense thermal energy. Without proper cooling, these high-end components reach critical thermal thresholds in seconds, causing thermal throttling, where the chip forcibly slows down performance, or leading to permanent hardware degradation and emergency system shutdowns. If you find this detailed breakdown helpful, make sure to like, share this video with fellow tech enthusiasts, and subscribe to the channel for more in-depth hardware guides. Heat transfer begins directly at the chip surface, where the integrated heat spreader, IHS, meets the cooler's base plate. Even though these metal surfaces look flat to the naked eye, they contain microscopic imperfections, air gaps, and uneven surfaces. Air acts as a thermal insulator and traps heat, preventing efficient cooling. Thermal interface material, TIM, commonly known as thermal paste, is applied directly between the processor and the cooler base. This paste fills those microscopic gaps and voids, acting as a highly conductive bridge that ensures seamless thermal transfer from the hot processor die straight into the cooling assembly. Laptops and ultra-portable devices face extreme space constraints, making traditional bulky heat sinks impossible to use. To overcome this, laptops rely on ultra-thin, flattened copper heat pipes attached directly to CPU and GPU cold plates. These hollow copper pipes contain a tiny amount of liquid, typically distilled water, operating under a partial vacuum. When heat reaches the cold plate, the liquid inside the heat pipe vaporizes instantly. This high-pressure vapor rapidly travels down the pipe toward thin aluminum cooling fins located at the exhaust vent. Once near the vent, small high-speed centrifugal blower fans force cool air through the fins, rapidly cooling the vapor and turning it back into a liquid. The liquid then travels back along an internal sintered copper wick to the heat source through capillary action, creating a continuous heat dissipation loop in a tiny form factor. Desktop PCs have much more physical space, allowing for larger and more powerful cooling setups like air coolers. Desktop air coolers utilize dense aluminum fin towers connected directly to multiple copper heat pipes radiating out from a solid copper base. As heat travels up through the pipes and spreads across the massive surface area of the stacked aluminum fins, large 120 mm or 140 mm high static pressure fans pull cool ambient air from inside the case, pushing it across the fins to dissipate thermal energy quickly into the surrounding air. For high-end or overclocked processors that generate massive thermal output, liquid cooling provides superior heat dissipation. All-in-one, AIO, liquid coolers and custom loops replace bulk air coolers with a specialized pump block mounted directly over the CPU. Liquid coolant, which has a significantly higher heat capacity than air, absorbs the thermal energy from the CPU block. The pump continuously circulates this hot fluid through flexible tubing straight to a large aluminum or copper radiator mounted to the computer case frame. Fans attached to the radiator force cold air across thin water channels and fins, cooling the liquid before the pump sends it back down to the processor block to repeat the cooling cycle. Individual component coolers can only perform well if the overall computer case maintains proper internal air circulation. System-wide temperature management relies heavily on optimized case airflow dynamics. Intake fans placed at the front or bottom of the computer chassis continuously pull cooler, ambient room air inside the case. Meanwhile, exhaust fans positioned at the top and rear actively push accumulating hot air out into the room. This continuous directional draft prevents stagnant hot air pockets from forming around the graphics card, motherboard VRMs, power supply, and storage drives. From compact copper heat pipes and ultra-thin laptops to high-performance liquid loops in custom desktop rigs, effective thermal management is essential for modern computing. Keeping operational temperatures within optimal ranges protects sensitive microelectronics, keeps CPU and GPU clock speeds running at maximum potential, minimizes fan noise, and significantly extends the lifespan of all system hardware.